Alrighty. 8.5, the second part, we're going to talk about scenario 2. So we're going to titrate with a weak acid and a strong base. And so here we go. Alright, so here's an experiment. So go ahead and just read that real quick. Cool. And we have this titration curve here. And so we can look at this and we can tell that we are starting with the weak acid in the flask because we're starting at a low pH. We have the sample and the sample, cool. And then we have the NaOH. Now notice it actually gave us the concentrations. So we didn't actually have to solve for it like the first scenario, but we could solve for it depending on what other information is given to us. For now, we're just going to stick to, hey, we have it. Cool. And so we're going to go through the different parts of this, and we're going to go through what each of the points on this graph means. And also we're going to talk about other things, like other stuff. And so this reaction, so we know a strong base is here, meaning it ionizes completely. And so here's my reaction. I 100% skipped doing the regular reaction and then complete ionic. This is the net ionic. It's the same as what I showed y'all in 8.4, so I'm not going to show it again. And so I just removed the spectators. Hooray. And so we have our generic ones with the weak acid and the strong base. Again, same thing as what I've showed you before. And so this graph is a little bit more complex, just a tiny bit, not significantly more, but there is some slight differences. So you could see the BCD points, that is marked for a reason. Okay, so as a reminder, the conjugate base can act like a base. So here's our conjugate base right here, the A- generic one. And so it can interact with water. And so you can make the weak acid again and the hydroxide. So that can happen. Okay, don't forget. Okay, so let's talk about this graph and what each of these points mean. So we still have the four main regions just like last time. So we have A, we have BCD will be considered one region, and then E, and then F. So those are still the four main ones. I'm going to be clumping BCD together, but talking about like each of those points in a second. So A is just our initial pH. Again, it's based off the concentration of the initial weak acid in this situation. Again, the 0 means initial. And then the Ka value for that weak acid. And so we would use the formula that I gave you before in section 8.4. In C, we are halfway to the equivalence point. And so at that point, the amount of weak acid is the same amount as its conjugate base, concentration. And so at this situation, we are using the HH equation that I introduced to y'all earlier. And this point C is very important. Being equimolar is very, very important to know because we are halfway to the equivalence point. So just make sure you know that that's an important point to know. Okay, and so we have regions B and D. Let's talk about point C first. Since we know that these are equal to each other, this part of the HH equation is 1, and so log of 1 is 0, so my pH is pKa. So FYI for that. So that's nice and easy. And so we have the other points, the point B and point D. Those are part of the buffer region. And so they're slightly over or under being equimolar, but they're still part of the buffer region. Now, I do want to remind you in terms of definitions that the buffer region is the area where the system doesn't want to change pH that much. It's going to interact with the weak acid or its conjugate base depending on what's being added to the solution, so the pH doesn't change that much. You can see here, BCD, pH doesn't change that much in that general area because again, it's a buffer. It's trying not to change based off that weak acid and its conjugate. So be mindful of that, okay? So don't forget. And so then we have point E. Point E is the equivalence point that we've talked about before. At this point, we have the weak acid and the strong base. The strong base converted all of that weak acid to its conjugate. And so that's why we're at equivalence at the point. Now, something very important about point E is that since we have only conjugate bases left of the weak acid, well, the conjugate base can still act like a base. And so the pH is more than 7 here. You could see it is past 8, near 9. And that's because, again, we have a conjugate base. The conjugate base is going to literally act like a base at that point. Okay? And then we have point F. We are after equivalence, so we have, more of the strong base being added there. So going back to point B real quick, we have more acid here than its conjugate, so we have more pK versus pH. Yep, and then point D is going to be the opposite. We have more of the conjugate base now in that situation, and so our pH is going to be more than pKa. And then if you're confused on why, think of what Ka is. We have products over reactants. Think of how we write this reaction. So it's stuff we've talked about before. So, cool. All right. What was I emphasizing for this? Oh, yeah. So pH at equivalence. Yeah, you know what I mean. So we have the weak acid and the strong base has its conjugate. The conjugate base is acting like a base, as I said before. pH is determined by the conjugate base concentration, and so we need to use the Ka value. We need to use the Kw value given on our constant equation to get our Kb, and this will make more sense as we talk about the actual calculations. Okay, and like I said here, pH is more than 7. Okay, cool. So the conjugate base can act like a base. Grab an H from water. Become the weak acid. Yay. Okay. I've talked about point F before, where it's just the axis OH minus. We'll talk about the calculations for that in a few moments. Okay. Before we do, we're going to recap our drawings. So you have your key, you have your graph. You see these different pictures, and you can decide which one is point A, B, C, D, E, and F. So look over the key, look over this. This is definitely something that could be asked on the AP test, so go ahead and practice by pausing this video. Okay, ready? Here we go. So I explained why. I have nothing else to say because I already explained it in the highlights. Make sure to ask if you're confused. Okay, so we're going to go through these different parts so you can see what kind of calculations they are. They correspond to various points of this titration curve, and we're going to talk about this in relation to the 8.4 pictures as well. So we haven't added any NaOH yet, right? And so that means we're at point A. So that's nice and easy. And so if you remember from our pictures on 8.4, we currently only have the weak acid. So we have this weak acid in the flask. And so if I go back to 8.4, we're in this situation. Okay? And so as a reminder for 8.4, this situation right over here, we only have weak acid. So there's only a few of the weak acids that ionize, right? And so the pH is going to be based off the concentration of the weak acid and its Ka value. So I set up a rice table because, again, we don't know how much ionizes, and we've done this math before in, I forget which section of Unit 8, but we've done this before. And so we're going to use our rice table. Again, we don't fill out water. This is just ionizing the weak acid, right? And so we're pretty much solving for the concentration of H+ here. And so we're going to use the Ka value because that's the equilibrium, because this is an equilibrium problem. And so I'm going to go ahead and have that here. Now I am rounding my E here to be approximately 0.2. Our Ka value is so small, if I multiplied that by 100, it's still way less than the initial concentration of the weak acid. So I'm going to go ahead and round that for simplicity's sake. Again, if you don't round with the shortcut, then you end up with a quadratic, which you could totally do. It's totally fine, but I'm not going to. So I take my Ka, remember it's products over reactants, so I have products here, it's Cn minus and H3O plus, there's no coefficients, so there's no powers here, and then I have my reactants. I'm going to plug in my value, so I have my x here, so x times x is x squared, I have my 0.2 approximation, and then I have my Ka value that was originally given up here. So that's my, where I got everything. And then I do my quick little algebra. And so my x value is, again, the same thing as the concentration of H3O+, because that's the point of the Rice table, is to get the concentration here. And so I do my algebra here. And then because I have the concentration of H+, I can plug that into the formula pH equals negative log of this value to get my pH. So I didn't show that, but we've done pH calculations before. So just make sure you can plug into your calculator negative log the concentration of H+ in order to get our pH. So, yay, easy. So again, we've done this before. Again, I showed you the picture on 8.4, so we saw that a little bit ionized, and so a little bit does. Especially compared to how much we have. We still have approximately the initial amount. Okay, now we're going to do part B. I'm going to show you the slightly longer way first, and then I'll show you the slightly shorter way next. Both give approximately the same answer. You have slight rounding errors, so you'll notice when we solve it the two different ways, my answers are going to be slightly different. College Board has a range for their answers when it comes to stuff like this, so you could solve it the long way and you still get the point, as provided you did it correctly, of course. Okay, so we are adding the strong base now. And so some of the acid has neutralized, but not all of the weak acid has neutralized. Only some. And so we need to figure out how much that sum is. And so the first thing I'm going to do is see how many moles of each of these compounds I have. And so I highlighted where I'm getting all these values from. And so I skipped some of the steps, like I skipped the conversion between milliliters and liters. It's the same thing, right? So there, right? And so I just plugged in, again, where I got all my values there. And so I have my moles of each. And so I'm setting up my BCA table, just like part 1's video. Now, I do want to point out, I did my BCA table slightly differently. I decided to do moles instead of molarity. It doesn't matter which one you do if you like setting up a BCA table. Okay, you could do moles if you want, or you can do the molarity of HCN and OH minus and then set this up. Same difference. It doesn't matter. As long as you don't get confused. That's the biggest thing. Again, I'm just showing a different way in case people like it. Again, if you prefer concentration, go for it. Especially because you're still going to set up Rice tables anyway, so you might as well convert it into concentration. But again, it depends on you. And so I look at how much strong base I used. So I used pretty much all of it. That's why it ends up being 0. And so because everything's 1-to-1, I could just subtract by the same amount of hydroxide. So cool. And so I'm going to go ahead and subtract and I get that value. I also get the conjugate base. Because remember, you are making the conjugate base. This hydroxide is grabbing an H. And so that's why it's now Cn minus. And then water is liquid, so we don't fill that out in the Rice table. Cool. And so I'm going to go ahead and get my new volume. So just like with the previous example, we have to get our total volume. So our total volume is, I could have color coordinated this. Oh, well, whatever. So our total volume is the 20 mils from the analyte, and then the 5 mils from the titrant, the NaOH. And so my new volume in the flask is currently 25 milliliters. And so I'm going to use that in my Rice table. So here I have my HCN over here, and then I divide by my new volume, and I get that. Wait, is that right? Is it? Whoops. For some reason, I put 100. I don't know. I just accidentally typed that, I guess, when I was editing these slides to color coordinate more. Anyway, so I have the moles from the after part because that's what we have. And then I have my new volume. And then I have my concentration. I also did the same thing here. I just skipped showing my work. So I put moles, these moles, divided by the new volume in liters to get my molarity. And so I do my rice table like I normally do. And so now I have to solve my rice table. And so I'm going to estimate these because, again, our Ka value is really tiny. It's 10 to the negative 10. So I could round these. Now, this one is slightly different than what we've done before because we always rounded the one that was subtracting. I can also round anything that's adding x because remember that this x value is going to be so little that adding any additional thing that's so little barely affects it, so I could just round it to 0.04. This x matters because we started at nothing, so don't round this to nothing, okay? Be careful. Okay, so I set up my Ka just like how I've set it up before, where it's products over reactants, so I didn't show that part. Make sure you do. So you make sure you put Ka equals H plus times Cn minus divided by HCN. That is 1 point on an FRQ. I just got lazy. And so we have 0.04 times x divided by 0.12. We got our Ka here from earlier. I do my algebra, solve for x, and as a reminder, x is H plus because it's right here on the rice table. And so I can plug that into negative log of this concentration and I'll get my pH. And there we go. So that's the long way of doing it. Okay. Now, the slightly shorter way is using the HH equation. So I still have the same setup. I still did a BCA table. I still have my rice table, except I'm not going to use Ka and like do the algebra where we did this here. I am going to go ahead and use the HH equation that I introduced to y'all in section 8.4 because we are in the buffer region because I still have my weak acid and my conjugate base of that weak acid. And so I can use the HH equation for that. And so as a reminder, we have our pKa. Remember, pKa is negative log of Ka. And then we have the log of A minus, and remember A minus is the conjugate base, and the HA is the weak acid. And so I'm going to go ahead and plug in the concentrations, which I have highlighted right here. And so I'm just emphasizing that, again, this is the conjugate base, so it's Cn minus, and then HA, HCN, that's the weak acid. And so I'm going to go ahead and plug those in. And so I forgot to put here negative log of Ka, but that's what's going to go there. And then when I plug that into my calculator, I get that. And so my number might be slightly off than the previous one, but there we go. So you could use the HH equation. You could not use the HH equation and just solve the algebra just like any other rice table if you want. So you have a choice. Do either one, as long as you do it correctly. That's always the biggest thing. It's like, are you doing it correctly? Mm-hmm. So be careful about that. Cool. But the HH equation is slightly faster, in my opinion anyway. But that's if you recognize that you can use it. So again, we have some of the weak acid and its conjugate base, so that means I can use the HH equation because we are in the bufferin zone. And so as a reminder, we can look back at where we are. So we are, adding hydroxide. We might not be fully at the buffer, like BCD area, or maybe we are, I'm not sure. But we still have the conjugate acid the weak acid and the conjugate base. Okay. So we are halfway to equivalence of point. We actually don't know that yet. I will explain why we do know that after we do the calculations. So we know we're halfway to equivalence point when we did the calculations, okay? I'm just pointing it out now, just so you know. Okay, so the HCN from earlier, so the hydrocyanic acid, We calculated this value because of the molarity and the volume. We multiplied those together when the units matched, and then we got the moles. And then here we have the OH, and we're adding 10 mils of that OH, so I converted it to liters here, and then I used the molarity that was given earlier, the 0.2 molar, and then I got my moles. My new total is 30, because again, you add the volumes up. We're assuming we started at initial 0, so that's why it's the full 10, rather than in the previous problem and then adding 10. So that's always implied. And here is my BCA table again. I decided to do it in moles. And so here is my strong base, and then it's 0. And then here is my calculations of just neutralizing hydroxide. So cool. So the reason why we know we're halfway to equivalence point is because we have an equal amount of the weak acid and its conjugate. Or I'm sorry. No. We know we're at the halfway to... I'm like looking at my highlighted parts, Okay, sorry. We're halfway to equivalence point because we used half of the weak acid. We neutralized half of it with the strong base. And so, because we used half of it, we're literally halfway to the equivalence point. The equivalence point for weak acid strong base curve is when we used all of the weak acid in the flask. So in this case, we used half of it, and so that's why we're halfway to the equivalence point. Sorry about that. It's getting late from recording this. Okay, and so we noticed that the HCN and CN minus is the same moles. And if I divided it by the V total, like the 30 mils, well, convert that to liters, the concentrations are going to be the same. And if I look at the HH equation, when the concentrations are the same, so these two are the same, it's negative log of 1, because when you have something divided by something and they're the same number, it's 1. And negative log of 1 is 0. So that literally just crosses out. So my pH is just pKa. So you take the Ka value and do negative log of that, and then you get your pH. So there we go. Cool. Cool. Okay. So next part, or next question rather, we are at the equivalence point. I'm going to talk about how we know in a second. I'm just pointing it out now, but you need to do the calculations in order to know. And so we have our HCN from earlier, again, same calculations, molar times volume, and then we have the 20 mils, and we convert it to 0.02, and then we use the molarity that was given earlier, and then we got our moles. I have my new total, again, don't forget that, and so I set up my BCA table like so, and so notice that all of the HCN and OH are gone, at least in this calculation part currently. And that's when I know I'm at the equivalence point. The amount of weak acid initially equals the amount of strong base that was added. So those are the same. The amount of moles of the weak acid equaled the amount of moles of the strong base, and so it was the weak acid was completely neutralized. So now I have the conjugate base. Now, the conjugate base is a base, so it's gonna act like a base. And so we need to set up a Rice table based off the fact that the CN minus is gonna act like a base, because that's what we currently have in this situation, because again, these all neutralize. And so I set up my Rice table with the conjugate base here. So we have the moles of the conjugate base, we have the new volume total, and we have 0.1. We don't know how much is going to, be at equilibrium with each other, and so those are 0. Again, we round this e to the 0.1, because when I solve for KB, it ends up being really small. So here's KB. The formula was KW is KA times KB, so we just reorganized it. We're assuming we're in room temp, and 1.62 times 10 to the negative 5. So when I do the shortcut, if I multiply that by 100, it's less than the concentration of 0.1, which is why we rounded this to be about 0.1. So I'm going to go ahead and plug that in to my KB, where I have my products over reactants, and so I plug in the values here. It's going to be x squared and the 0.1. I have my KB here. I'm skipping all those steps because we've already done this a million times. And so I solve for x. The x is the concentration of OH minus, which is that, and then I could get my POH from negative log, and then I have my pH plus POH is 14, so then I can get my pH to be 11.1. Whew! So, quite a bit of math. So be mindful of that. Again, the calculations are the same as what we've done before. We just have to keep in mind that the conjugate base in this situation is going to act like a base. So we have to use the KB because it's acting like a base, and then use that to solve the rice table. Cool. Okay. When we're adding 25 mils, pH depends on the excess base. Oh, actually, before I even talk about party, or maybe, nah, never mind. Okay, so, pH will depend on the excess base, since we know we passed the equivalence point, at this point. The equivalence point was 20 mils, because we literally saw it here. This is equivalence point when we use up all of the weak acid. So keep that in mind, that again, if I reach this problem where I didn't solve for equivalence point before, solving for equivalence point helps to know if I went beyond it, or if I'm before it, or if I'm at equivalence point. So it's a good thing to calculate just in general, even if the question wasn't asking for it. So you can use it as a reference point. Okay, so since I know we're past the equivalence point, we use 20 mils from, the previous part. That's where equivalence point is. We added 25, so I have 5 mils of this strong base left over. And so I see how many moles of hydroxide that is. And then I have my new V total. Again, V total is based off adding the 20 mils from the flask and the 25 mils from the burette. And so my concentration, I just divide the moles by the liters to get molarity, and then I get my POH from negative log of the concentration of OH minus, and then I get my pH from pH plus POH is 14. And so we calculate pH to be 12.3. Yay. Okay, here's a quick your turn. Should be quick. I even tell you when does that occur. So like there's only one point you're calculating. So see if you can figure it out. Pause it. Okay, ready. Boom. So the weak acid and the strong base neutralize each other at equivalence point. And this only works if it's 1-to-1, so I pretty much did the shortcut way of doing it. I could have shown all my work just like the previous example, but I'm just showing you another way of doing it. Again, this only works if everything's 1-to-1 in the reaction. If you have a coefficient in the front, then you need to do the stoich like how we did the stoich before. Okay, that's going to be it for part 2. Okay, bye!